welcome to Module 31 on backpropagation and automatic differentiation. So this module is going to be a little bit atypical. It's both going to be relatively long in terms of the number of slides, but hopefully we can get through it fairly soon. Throughout a lot of this class, I try to relate the mathematics and the code and to try to demonstrate that these are often just two views of the same phenomenon or the same method. You can't do the math well if you don't know how to code, and you can't do the code well, especially if you don't know the math. That's an important thing to remember. This slide deck is going to be somewhat more mathematical, a little bit more theoretical, but we're going to touch towards the end on PyTorch and mention how PyTorch implements a lot of the mathematical ideas we'll be talking about today. I want to reemphasize that we're going to go through it fairly quickly. There's going to be a lot of math in this, a lot of calculus. Not all of the details, I can tell you, are going to be practically important for you in this class in terms of things like quizzes and assignments and that sort of thing. But nevertheless, like I just mentioned a moment ago, if you want to be a good coder in machine learning, it really does help to know the mathematics, so we don't want to skip this. Just generally, the learning outcomes today are going to be to explain the idea of a computational graph, what a forward pass is and what a backward pass is. A lot of the math is going to be in the form of the chain rule of derivatives, so we're going to derive gradients in a small feed-forward network. We'll actually implement that from scratch. A bit of a stretch goal is to implement manual propagation for a toy MLP. I just said we're going to do it ourselves. It'll be on the slide deck, but whether or not you can do it at the end of this module is a bit of a stretch. But verifying, comparing two approaches, one fully automatic, one manual, to backpropagation is something you should be able to do. You'll be able to use an automatic differentiation framework to train the same model and interpret it. It's how its machinery worked in terms of its gradients, and you'll be able to diagnose or at least identify some gradient-related bugs, like wrong shapes, forgetting to reset gradients, and so on. So there's a bit of motivation. We know how to train simple models like logistic regression, and we know how to do that with gradient descent. We saw it at the fairly early parts of this class. Now with neural networks, the loss at the end of a kind of feed-forward process will depend on all of the parameters in the neural network at many layers of composition, potentially many, many layers of composition. So generally we have this idea that we have a function that's in terms of its parameters that we want to optimize, and that can be expressed as the loss function between a prediction and the desired output. So nothing new here yet. So the naive approach would be to differentiate this entire expression hidden here behind this right-hand side by hand. For every neural network, you'd have to compute what the gradients are specific to that network. This is going to be very tedious, error-prone, and would have to be done for every architecture. But then in comes backpropagation, which traces some of its origin back to this landmark paper from 1986, which is a generalizable recipe that can compute all the gradients you need locally and efficiently. It will be able to reuse intermediate qualities from the forward pass. So when you're making predictions, you can store a lot of details and then use those details when you're updating the weights on the backwards pass. And it's at least the theoretical aspect of what we're going to talk about is below, underneath a lot of modern deep learning and auto differentiation libraries. So as usual, the conceptual scaffold. So we want to define a computational graph. A computational graph here is going to be expressed as a directed acyclic graph. This is just a graph of nodes and edges. The nodes represent variables, intermediate values. In some cases, there's sort of a function, like input goes into this node and an output comes out. The edges represent sort of a mapping. It's sort of a function going from one node to the other. And they're going to be directional, so they're going to go from parent to children. And because it's acyclic, when you look at this entire graph, there's going to be no loops that you can't get back into the node by following a series of edges, directed edges back to the same node in the same pass. This is actually giving me two computational graphs, but both of them are acyclic, like more or less one directional. There's going to be a forward pass and a backward pass, like I just alluded to a moment ago. In the forward pass, we evaluate the graph from the original inputs. So we have a some input variables x, we push everything through to the output, and then we can compute a loss, which will also be represented as a node. And as we do that, we can store intermediate results. And then there's a backwards pass where we propagate derivatives backwards from the loss back towards the input variables x. It'll be more or less of this form. You're going to see a lot of this today. I'm going to call this DL D node or delta L delta node. This is just the derivative of the numerator with respect to the denominator or the variable in each. We're going to see the chain rule a lot. I'll remind you of what that is. So the local gradient is going to be this derivative of a node with respect to its immediate parents. So we don't need to compute things globally. We can compute small local derivatives just in terms of nodes, in terms of their adjacency of this directed acyclic graph. And backpropagation is going to multiply these local gradients along these paths. I'm going to mention this probably later, but obviously this module is coming up in the context of neural networks. You know, like a lot of this is just neural networks focused, but I'm going to try to mention that a lot of what we're doing here is generalizable. So one of the reasons we're using these directed acyclic graphs instead of specifically talking just about neurons and layers is because this approach is a very generalizable approach, and it works on other kinds of computational graphs that need backpropagation of derivatives, not just neural networks specifically. This is a nice generalizable result, a nice generalizable series of techniques. So here's a directed acyclic graph formed of these nodes and arrows between them. So we have inputs x as usual. Those are over here in blue. So these are just input variables of a two-dimensional feature space. We have an output y, which is over here in green. That's just a binary target variable, nothing new so far. We have our parameters, w sub 1 and w sub 2, up here in yellow. These are real values. These are weights applied to each of our input variables. So far, again, as usual. And this again applies to neural networks and various forms of regression. We have our bias unit b, which is down here. So a weighted combination of x plus b is what we've been using for our a linear model, giving us overall linear function z, which is down here, intermediate quantities, which is this purple node, which I'm pointing to. We have additionally, more parameters we can adjust. There's a weight for a hidden unit, which we'll get to in a second, which is v, which is down here in deep yellow. And then we have c, which is another bias term. So all of these yellow weights and biases are things we can adjust. We've computed the linear combinations of x's with their weights. These are going to be passed through a sigmoid function, giving a hidden activation h. So the sigmoid is represented here by sigma. Z is what we've computed in the previous point. So you can see how information passes through the graph, right? So we have inputs and weights and biases. That information passes forward through the network into this intermediate representation Z. That intermediate representation Z passes to the sigmoid function, which gives us H. Actually, this is more correct, what was actually written on the previous slide. These edges represent the functions themselves. So going from Z to H means pushing Z through the sigmoid function sigma. So now H is a representation H. We have additional layers, so whatever we get from that sigmoid, we also pass through a linear function. There's the weight function, weight vector v. There's a bias term c. Those are our parameters. We get a linear transformation giving us u. U is also pushed through a nonlinearity. We mentioned in the past module why nonlinearities are so important, and that finally gives us our prediction y, a hat, which is sort of a probability for class 1. The probability is high, we think it's class 1. It's low, we think it's not class 1, i.e. it's class 0. And then finally we have this kind of special node over here, which is L, which is the binary cross-entropy loss. I mean, in this case, it's a binary cross-entropy loss. You can replace this with a mean squared error loss or whatever the occasion calls for. But because this is a classification problem, like I mentioned a second ago, we have predictions that are on the sigmoid, so we're doing logistic regression. It makes more sense to use the binary cross-entropy loss, which we've seen previously, which is shown down here at the bottom. Which is a combination of whether or not the class is positive, which is the first term, or negative or 0, which is the second term. So we've seen this already also. So far nothing new. This is just conceptually, we're representing everything we've seen previously in terms of it as a series of equations in a graphical form, right? And information is kind of passing forward through this network as we're going from the inputs to our eventual computation of the loss. So because we're going to need this in a second, I want to go back to the chain rule. We actually talked about the chain rule actually in another class entirely applied to probabilities, but you remember how you can take like a factor and break it down into a bunch of subfactors. There's a chain rule in probability. There's also a chain rule in calculus. So the chain rule in calculus basically means turning in a differential into like components, breaking it down into a few factors that are easier to compute. So imagine, for example, that z is a function of y and y is a function of x. Then if you want to take the derivative of z with regards to x, then what you can do is take the derivative of z with regards to y, because we have this direct function, and you can multiply that by the derivative of y with respect to x. And just like a lot of rules of arithmetic, this is great because you can see how like dy on the numerator and denominator kind of cancel out, speaking loosely. So like visually it looks like a regular product of arithmetic. dz dx is equal to dz over dy times dy over dx. For a computational graph, each node will have some value. I'm calling it v here. So v, like I'm using u and v here, again, because there's only so many Latin and Greek characters, we have to kind of swap their names sometimes. They're not typed, so to speak. So anyway, each of our nodes will have some value we call v arbitrarily, and it'll have multiple parents. We call them ui, like u1, u2, u3, and so on. And then we'll have local gradients. So we'll have the derivative of v with regards to ui, where I is 1, 2, 3, 4, however many parents there are. And when we're trying to compute backpropagation, we have the loss, which is the last thing we computed in a graph, and we can represent it in terms of, we can take the derivative with respect to u sub I if we know the derivative of L with regards to v, and we know all of these local gradients v with regards to du sub I. Nothing really special here. We have a very simple chain rule. This is a generic rule of calculus. And we have, more specifically to our computational graph, we have a loss. And we want to find its derivatives with regards to a bunch of aspects of our graph. And we can use the chain rule in order to get those derivatives precisely. So one thing we can do, given that we're thinking of things in terms of a graph like this, it helps to think of the loss function, or the derivative of the loss function, as a message that we're going to push backwards or let it flow backwards through the graph, just in the reverse order that we see here. And these messages will be kind of scaled, and these scales will be the local derivatives. Okay, so we're going to see an example of that fairly shortly. So starting to like visualize things a bit more like a neural network. Like now we're looking at like the same graph as before essentially, but just structured, hierarchically like a neural network. Here, inputs come in at the top, and we're going to push the information through the neural network. So we have x is passed through a function f, giving us z is passed through another function g, giving us h, and then h is pushed through some final function script l, which gives us y. There's going to be an error there, a loss, and we're going to push that error back through the network in just the reverse order. We want to take, in this case, the derivative of the loss with regards to h, which is the next variable here, and then we want to take the derivative of L given z, which is the next one, and then derivative of L given x. Okay, so eventually we want to make modifications to all of our weights at each of these layers. We want to kind of compute these partial derivatives, keep them at each of these layers here, and then apply them to our modification of the weights. So in the forward pass, essentially we have any of these nodes will be some kind of function f that'll be in terms of a bunch of inputs, u. A bit confusing here, this f applies to both this f in the graph and this g in the graph also. So in both cases, these are nodes. These nodes are just represented as functions of inputs, which are sort of the parents in this graph. So h is a function of z is a function of x, and so on. When we're pushing things through the graph, we're going to store both the value we've computed, v, and often we're going to store the pointers to the parents. We're going to need that if we're going to do backpropagation properly. In the backwards pass, this is the message passing. We're going to kind of like divvy out the blame for whatever goes wrong at the output, the last layer. We're going to start divvying it up and then separating it and pushing the message backwards through the network and flowing everything back towards the beginning. So by the time we've visited v in backpropagation, we already know its gradient. We already know dl with regards to dv, and we know that because we've computed all of the partial derivatives in the higher order nodes. So if you know dl with regards to dh, that is what you need in order to compute dl with regards to dz, because you also know the derivative of z with regards to h. Sorry, h with regards to z. So yeah, for each parent u, so everything kind of further back in this network, we want to compute the contribution from it through intermediate nodes v all the way to the big loss L. And this is what I just mentioned a moment ago. You have this message which goes from v to u sub I, and that's going to be the derivative of L with regards to v times the derivative of v with regards to u sub I. Right? So I want L with regards to u sub I, and I can construct it using the chain rule out of these partial derivatives. Then we're going to accumulate this into the parent's gradient. So we have some pre-existing knowledge of the gradient, and then we're going to keep on adding these partial derivatives from parents. This is more of an implementation thing we'll see later on, but like this looks like code a little bit. We're going to have this this quantity on the left is going to be composed of these two terms on the right. Just like when you're kind of summing over a list, or in a for loop, you're kind of accumulating some overall sum or quantity. The same thing's going on here. For each of these intermediate nodes here, we're going to kind of keep on adding these messages on the right-hand side here, this second term, to whatever we've accumulated so far, and this will all add up to our overall loss with regards to each of our values u sub I. We follow the reverse topological order. So first we process nodes from the outputs back to the inputs. This is where the term backpropagation essentially comes from. Every parent will collect contributions from all of its children. Right now, each of the parents in this graph, that is to say each node closest to the input, has only one child, that is a node closest to the output, as you can see here. But this equation that I just mentioned sort of generalizes in situations where parents can have multiple children. So an input can be passed to multiple subsequent layers of in parallel in the network. So the key idea here is that backpropagation is essentially just message passing. Every node will send a gradient message to its parents backwards towards the input, and each parent will sum all the messages it receives. Just a little bit of more detail. So I kind of hinted at the fact that, like in general, we don't have to have a graph as simple as this. We can have graphs that are a little bit more complicated, in which a node in which we've computed u can be used in a couple of different places. U can be passed through a function f, giving an intermediate value v, and u can also be passed forward through another function g, giving us an intermediate value w. And then both v and w can both be used in the computation of some kind of loss. I mean, this is super simple. There's probably other variables here that you need to measure, but the point is that we're not really constrained to have like something as linear or as simplistic as this graph. Occasionally you have multiple parallel hidden layers that you might have in a neural network, for example, and this just shows that a layer L information can be passed to two separate hidden layers at step L+1, if that makes sense. So what we've been doing is with this accumulation over here is essentially what this addition is doing over here for this very simple graph. We want the derivative of the loss with regards to u. The loss is kind of the last node in our forward pass, and we want to pass the information back towards u. We want the derivative of L with regards to u. Well, we need to do this in two steps. We need the derivative of through v, and we need the derivative through w. So we have the derivative of L with regards to v times derivative of v with regards to u. That's going to give us one quantity plus the derivative of L with regards to w times the derivative of w with regards to u. And both of these things together will give us the overall derivative of L with regards to u in both of those directions. Again, not to speak, like, we're getting kind of detailed here, but if this is a neural network, you're going to have some weight matrix between U and V and another weight matrix between U and W. And those will be set through the learning process, and whatever in the forward pass results in some kind of loss that we don't like and we want to minimize, then one of those through two passes towards the output, towards L, will be more responsible for the error. So we'll have some blame coming through V, some other proportion of the blame coming through W. This will help us to assign blame on each of those paths separately, but both of that blame can be applied to the origin U, which is sort of at the origin of both of those paths. So we need to just sort of accumulate all of that blame through this summation. And as you probably know, I can imagine if you have, like, this generalizes to many more paths. So if we had a third path to some third node, call it omega now for argument's sake, there'd be a third term that would pass the loss function towards U through W. So with regards to W and with regards to omega, and with omega with regards to U. So this is kind of code-ish. Initially what I'm trying to figure out, what is the derivative of L with regards to U, I can set it to 0, and when the backpropagation visits V, when I'm pushing the blame or these gradients backwards through the network, I have what I've accumulated so far, which might be 0 initially, and then I add the derivative of L with regards to V times derivative of V with regards to U, and that adds to my running total of L with regards to U. And then when I visit W, then I add its component to my running total. Okay, so everything here in message passing code form is essentially just implementing what we have in here in the chain rule. So this is not complicated at all. This is kind of first year coding stuff. If we want to have a sum of partial sums, we'd start with 0 and keep on adding to the accumulated sum every time we want to add another term. Okay, so there's only one thing happening here, really. After both, in this graph, or let's say all in general messages have arrived at a particular node, then the stored derivative of L with regards to U, with regards to that node, is now the full derivative, accumulated from the future, from the output towards me. And then, so basically every child of U, or every node subsequent in the neural network, has passed the message to me, U. We just simply add up the gradient, giving us the gradient of the loss with regards to us. This is going to help us to apply blame to nodes that came before us, to our parents in the computational graph, and then we push the gradient backwards to the graph to our parents. That is to say, nodes that came earlier in the graph in the feed-forward pass. So there are always things you can do wrong. The one thing you can do is you could do what we're doing now, actually, and derive the gradients on paper for a very specific network. Like, a lot of what we're doing is for a particular computational graph with a particular structure to it. Maybe there's only one hidden layer because we're doing something very simple. And then we hard code the formulas. We hard code everything we just mentioned a moment ago. And that's obviously going to be faulty. We may want to add additional parallel layers. We may want to add like deeper layers, like more children, like a more complicated graph. We may want to change activation functions, G or F, and so on. So all of the subderivatives themselves will change. We want to just be flexible in terms of our coding. Any kind of hard coding we've done before will have to be completely redone, which is totally inefficient. Because our gradients that we've computed won't match the computational graph, and training will behave strangely, is putting it lightly. It'll just be incorrect more specifically. So what we want is a backpropagation of these derivatives to be general. We want like a general approach on graphs generally, not just a single one-off symbolic computation that we happen to compute for a particular neural network that we've implemented at the moment. So modern frameworks will actually build the graph at runtime and then push information forward to the graph like we alluded to earlier, and then rerun backpropagation automatically during the learning phase. So getting into the details a little bit more, we have a feed-forward neural network, a multi-layer perceptron, and we want to compute some gradients. So we have a single training example. We have input x, we have output y. X is a vector, as usual. It's a d-dimensional vector of real-valued numbers. We have a hidden layer. The hidden layer will basically pass our inputs through a linear transformation, like we've seen several times. There'll be a weight matrix, a W, which can be like an M by D matrix. And then we'll have a bias term, R of M. For what it's worth, M is a parameter we can change, which would, change the dimensionality of our data. We spent some slides talking about dimensionality reduction, so nothing new here so far. We take this linear transformation of x, which we call A. We pass it through a nonlinear transformation, which we like to have because we're using neural networks. Now we're just going to use a sigmoid function represented as sigma, giving us a hidden layer, H. Then we're going to have our output. We're going to do binary classification. We're going to do another linear transformation. We have a new parameter set V, which is an m-dimensional vector. We'll have another bias term, and this will give us U. U will be passed through another sigmoid, and this sigmoid will give us our output Y hat, our prediction of the probability of the class being 1. And then we have our trusty binary cross entropy loss, which is down here, which is, again, there's two possibilities. Either the Y is correct or it's incorrect. So those are the two terms here we have in this loss function. We've seen this before as well during the logistic regression phase. It applies to neural networks also, obviously. So our step 1 is to compute the gradient at the output. So for logistic and the binary cross entropy loss, we have we have a key simplification. So the prediction is going to be just a sigmoid function of the intermediate prediction U. This is the sigmoid function, nothing new here. Technically, you can sometimes add extra parameters to the sigmoid function, but this is like the default sigmoid function. So we've computed U a moment ago. This is just a linear combination of the hidden layer and some weights. So we have a single training example. So we're just computing the per example loss. And we know we have a sigmoid function. This is our loss function right here, which we mentioned a moment ago. I'm skipping a whole lot of steps right now between this thing on the left and this thing on the right. I can leave it as an exercise for you if you really care to look into it, but you can also just believe me. The derivative of this loss function with regards to U, which is here, which is part of Y hat, which is here and here. You can go through the steps yourself if you want, but you can convert through the chain rule. What is dl with regards to du? Well, that's the same thing as dl with regards to y hat times d of y hat with regards to u. So you can compute the second of those two factors is just the derivative of this term up here, this fraction up here, which I'll actually define in a second. There's a super straightforward way to find the derivatives of sigmoids. And then you have dl with regards to y hat, and you probably know enough about derivatives of logs and minus logs and fractions of logs and so on to compute that first factor in the chain rule applied in this arrow over here. Anyway, those are all hints. If you really want to go through the steps yourself, it's perfectly reasonable for you to do that. It's fun and it's entertaining, and it gets you a bit more close to the reality of what's going on, and it reminds you of how the chain rule works and so on. But you can also just believe me, and you can just believe me that the derivative of this loss function with regards to u is just y hat minus y. Super, super simple. So we're going to later use mini batches. We've talked about mini batches before. So this gradient in some code is going to pick up an extra factor 1 divided by n. I'm just mentioning it here because later on we're going to see this exact step in code in Python, and it's going to be confusing, where did this 1 minus n come from? I thought it was just a simple subtraction, so I'm just warning you ahead of time so it doesn't seem weird later. Because we're doing logistic regression, this y hat minus y term will appear in a lot of different scenarios, not just the specific one we're implementing right now, but even softmax models as well. So we're going to keep on propagating backwards to v and to h. So u was like the input to our last sigmoid function. That was just a linear combination of h. We have local gradients. So what is the derivative of u with regards to v? It's just h. What is the derivative of u with regards to h? It's just v. And what is the derivative of u with regards to c? It's just 1, which is not shown here. So we can take the backpropagation. So again, like if we want to compute the derivative of L with regards to V, we can apply the chain rule. We already know the derivative of L with regards to U. We just computed that a moment ago. It's y hat minus y. We know the derivative of U with regards to V from our super simple linear function. That's just h. And then multiplying these things together gives us this right-hand side. The same exact logic applies to this second computation for the derivative of L with regards to h. And then finally, the derivative of L with regards to c, which is also a parameter we can learn. Apply the chain rule. That's just the derivative of L with regards to u, because the derivative of u with regards to c is 1. So far, so good. Now, we keep on backpropagating information backwards towards the inputs. We still want information about w and b. So we have, we know that h, which we are previously, we're previously at node h. H came from a sigmoid function applied to a, and a was a linear transformation of our inputs x using a weight matrix w and our bias b. Again, we've seen this a moment ago. There's element-wise, functions here. So for every activation a sub j, this is passed through a sigmoid, giving us the hidden value h sub j, and so on. And j is just a row of w. So we have local gradients for each of our values or variables. So the derivative of h sub j with regards to a sub j is the derivative of sigma given a sub j. The derivative of sigma is often just simplified as a sigma prime over here. This is what I mentioned a moment ago, like the derivative of the sigmoid function. This function over here has a simple form which you might end up just memorizing like I did, like many of us do. It's easy to look up. It's just sort of the thing we've computed times 1 minus the thing we've computed, and the thing we've computed is h, so it's just h sub j times 1 minus h sub j for each of these derivatives. So this is one of the reasons why people like sigmoids, is because the derivative is so easy to compute, especially if I've already computed h sub j during my forward pass. When I'm doing my backward pass now and I want to accumulate all of these derivatives, I mean, I've already computed everything I needed to do. All I have to do is one multiplication and a subtraction. Anyway, so we're still pushing things towards the weights. So again, I'm going to skip things for brevity here. Like, I'm just going to be repeating myself over and over again. It's just the same old thing over and over again. I want to compute the derivative of the loss, like the last a node in my graph, in terms of nodes earlier and earlier in my graph. I just keep on applying the chain rule over and over again. And I have all of these very simple factors here. They're computed in different ways. Here I'm happy to take advantage of the sigmoid derivative. In the previous slide, it's really easy to take derivatives of linear functions like this. We know how to do that already. So we just keep on applying all of these chain rules one after the other, and at the end we end up with what we've looking for this whole time, which is the derivative of L with regards to W, which through the same kind of sequence I've hinted at repeatedly, this ends up being the derivative of L with regards to variable A times whatever the inputs were. This came up in class the other day. I'm skipping over a couple of things here. Like I mentioned a moment ago that you'll probably know the derivatives of logs, but in case that's not true, let me know. Somebody asked about what this t is. This t is just the transpose, and this is how I zoom out, like so. And so, I mean, sometimes in textbooks even, but often in slides like this, this transpose is not shown. because it can confound people. Like is it to the power of t, or is it something with regards to time t or something like that? It's not t. It's not. It doesn't look like a capital T. This is just the transpose of a graph of a vector. You can also apply transpose to matrices, but the reason we're applying transposes to vectors is just because when you're doing vector multiplication, you're having to sum over the columns of a row vector and the rows of a column vector. That's the only way to multiply these vectors together. Regardless, we've come to our goal. We've represented the derivative with regards to our weights W, which are the earliest parameters we can modify in our computational graph, and we've done so by accumulating through a chain rule a lot of sub components, a lot of partial derivatives, and we have, like this, the original inputs that we were given in the first place. So automatic differentiation, or autodiff, which will come up again a few times, is a way to automatically compute the exact derivatives of a function, like this one, implemented as code, like we saw a moment ago, using like summations over children, by applying the chain rule along a computational graph. So again, like even though there's probably some points here where I might have lost some of you in terms of like what exactly I'm doing in each of these steps, the overall message should be fairly clear. We're pushing information forward through a graphical structure, and the idea here is that it's a neural network, and then we're storing partial computations along the way. And then we want to push information back through the network during backpropagation so that we can make modifications to our parameters. So we need to have derivatives of the loss of the error that we're making with regards to whatever variable we're trying to update, such as the weight matrices. And we have to just push that through the network. We talked about a couple of ways that we need to do this. One is through the summation or the accumulation of partial derivatives on children nodes, if a parent node has multiple children. And then we also showed how you can take the derivative of a downstream variable like the loss in terms of a earlier variable like weights, in terms of partial derivatives, which we can just multiply together through the chain rule. Okay, so big picture, it's fairly straightforward. The details need to pay attention to, and hopefully I didn't mislabel anything as I was giving this sort of description, but big picture, I think it should be clear. At least I hope it is. So I want to mention briefly reverse mode versus forward mode auto differentiation is what we've been doing. Forward mode auto diff basically tracks how each intermediate changes with respect to a small set of inputs. So this is when you'd use this when you have a few inputs or many outputs. Reverse mode autodiff or backprop tracks how scalar outputs, like a loss, changes with respect to many inputs or parameters. This is reverse mode autodiff is what we're normally doing in neural network training. This is very good if you have many parameters like we have in neural networks and one loss. You can have multiple losses in neural networks, but often we have one classification loss, or it's a regression loss, or it's a cross-entropy loss generally. So this is what we're dealing with in most deep learning settings. And then modern ML libraries, which we'll come back to again at the end, like PyTorch specifically, or a few others. Basically, when you're doing machine learning training, it'll construct a computational graph according to the architecture or the topology you provide, the code. And then it'll store intermediate values during the forward pass, and then it'll do like operations, intermediate values, and use those when it's doing its backward pass during the learning phase, during the backpropagation phase. Hopefully some examples will just illuminate any kind of dark areas that you might still have. So here's, again, the moon setup. I'm probably going to move away from the moon fairly soon, but I wanted to stick with things so that we have a bit of continuity. Nothing new here. We just have the standard moon data set from sklearn. And we know what it looks like. I think there's a bit more noise than usual because now we have some overlap. We have some purple class in here amongst the yellow class, which we've previously mentioned is somewhat more challenging than the non-noisy case. We're going to have two input features. So actually right now, we're going to be doing everything by hand. This is something that like a lot of machine learning classes just did by default. It's starting to disappear a little bit in a lot of other machine learning classes that I'm aware of, and people just want to just do everything superficially. But so again, I mentioned at the beginning of this class that we're going to be going into a bit of detail here that might not come up in a day-to-day sort of thing, but it's kind of like the why am I learning this math when I'm never going to see it in my daily life? Like, it's still good for you. It's good to eat your vegetables, and I'm going to try to mention a few instances at the end of this lecture where it's still good to know how everything works step by step. And spoiler alert, it's going to have to do with debugging and identifying potential problems in new approaches that you might be implementing yourself as you deepen your careers in machine learning. So anyway, this is going to be a very manual process right now. So we manually define the sigmoid function. Here we manually define the derivative of the sigmoid function. Here, so we saw this in math a few moments ago. It's just like what we've computed times 1 minus what we've computed. I made a little note here. This is not great. Maybe I'll try to fix this later, but like normally, like the whole point of doing the forward pass is we're going to be pushing information through the network, and then we're going to be storing intermediate variables, intermediate values in the nodes of the graph. So somewhere there's a sigmoid function that goes into an intermediate value node. I want to store S in that node and just keep it there in memory. And then when I come back to it during backpropagation, I'll have already computed S. So I don't need to do this whole computation again. In general, in a proper implementation of what I'm talking about, this will all be stored in some big matrix. But for simplicity, in terms of just the code, I'm not going to do that. So we have to like compute S by running the sigmoid again. Again, I'm spending too much time on this. There's more efficient ways of doing this, which is always more efficient is always better. With caveats, I guess. But here, like, just anyway, to keep things simple, we'll have to rerun the sigmoid within the derivative. We have our binary cross-entropy loss, which takes a prediction and a true value, and it returns the old familiar function, which we've seen several times. We have the input dimensionality. It is 2 dimensionals, like the moon data is 2-dimensional. We'll have 8 hidden units. Let's see, what else are we doing? We're initializing our parameters. So W and V are initially going to be sampled from the normal distribution. The biases B and C are just going to be zeros, a vector in the former case and just the scalar 0 in the latter case. And then we have our forward pass. Our forward pass is the product of X and the weight matrix. Then we pass that, and we add that to the bias. That's going to be, this is a linear transformation. We pass that through the sigmoid, or nonlinear function, which gives us our intermediate value H, which is still the 8-dimensional hidden vector. And then that is multiplied, that hidden value is multiplied by another set of weights added to another bias, giving us U. And that linear transformation is passed through a nonlinear function, another sigmoid, giving us our predictive probability. And then at the end of all of this, we have all of our intermediate values here, including our prediction y hat. I just wanted to step through this just to kind of hold hands, I guess. Like, this is nothing fancy here. I'm not doing any magical tricks in terms of what we're talking about. Like, I want to emphasize that even though like we're reframing things in terms of computational graphs and in partial derivatives and the chain rule, like so far everything is super straightforward. So we're going to do one training step with manual backpropagation, and that's what it looks like here. So one training step, we'll have a batch now, which I warned you about, which will have a few input variables. We'll have n of them, a few y's in the batch, and then all of the intermediate, like the weight vector, the bias, everything that we have before. And let's see, LR is, yeah. So we do our forward pass. We get all of the intermediate variables that we need soon enough. We compute our loss, which again is just a comparison of the predictions with the true values. This gives us our loss. And then we do the backwards pass. I'm going to step through this a little bit quickly. the comments here should guide you in terms of which each of the steps are. I said I'm going to walk through it quickly, but I imagine I'm not going to. Remember from several slides ago, we mentioned before that the derivative of L with regards to U is just this very simple difference. And I said, this comes up all the time in different functions. And then I warned you, like, by the way, all of a sudden there's going to be this weird divide by n factor in this computation, which seems to come out of nowhere if you're paying attention. This is because we're doing a batch now, we're not just doing one loss for one variable at a time, but we're computing over a batch. We're taking the averages. So this is going to be just given all of the, a vector y hat and a vector y batch, we'll take the average of these, and this will give us the dl du. Then we still want to push the loss backwards through our networks. Again, in the computational graph, we have u is expressed in terms of the second set of parameters v and the second bias term c. And we know how to compute those. Like, this is something we showed in math earlier on. So this at sign is a product. This sum is just the numpy sum. And this gives us more partial derivatives. We still want to keep on pushing things backwards. So what is the derivative of the loss with regards to the intermediate value h? We get this through this outer product here of dl du, and which is over here, and v. And keep on pushing. Like, at some point, we need the sigmoid derivative, and we know how to compute that because we have that function on the previous slide. Keep pushing things back through these chain rules and these sums, and eventually we have our actual gradient step. Remember in the previous module we talked about updating the parameters of our neural network. We have our original weights, and then we subtract some learning rate hyperparameter times some change. Back then it was only the difference. Now we're dealing with derivatives. So these 4 lines are basically that one line of learning from the first neural network, the previous module, the first neural network module. So our weight matrix becomes whatever the weight matrix was before, minus the learning rate times the derivative of the loss with regards to my weights. My bias term b is whatever the initial bias term b was, minus the learning rate times the derivative of, again, the loss with regards to me, the bias term, and so on, right? And this is actually where all the learning is actually happening. So this is kind of the culmination of the whole story. We want better weights, biases, and weights and biases. And so we need to take what we have previously, we update them according to the derivative of the loss, of the surface of the loss towards the optimum. We do so by multiplying by this learning rate, which we've called eta in previous modules. The learning rate is just a parameter, that hyperparameter that we can set ourselves. And that's kind of it. This is one training step. So, when you're doing training, it's an iterative process. You do this many times, but this function just allows us to push a loss for a particular batch back through the network and then adjust our weights and biases for that batch. We're not finished. We have to do that over and over again, continuously updating weights and biases until we're satisfied with our solution. So here's the code for the big picture, the manual training. We have all of our training data. We have some validation data, so some data held out for validation. We're going to do 200 epochs. So that thing we just did, we're going to do up to 200 times. Our batch size is going to be 64, so that was kind of hidden to us before because we were just given the batches themselves. N in this case would be 64 because I passed it over here. Here's our learning rate, which again we can set by hand or we can optimize through some hyperparameter optimization. I might just leave this for you as an exercise to just walk through this and make sure that everything's sort of making sense, but there's nothing really complicated here. There's a for loop that runs through all of our epochs and the number of epochs we want to run. And then for every epoch, we just shuffle the data, we pull out a batch which is here, and then we pass that batch to our training step, which we just walked through on the previous slide. This will give us, a loss on the that batch, and new weights, biases, and so on. And that's it. And we keep on going, through all of our epochs, and that's essentially it. I think, is there anything else to mention? No, like we can keep on, our weights. Okay, so here's where we provide our weights. So initially this is global. We set these to some random variables initially. They're set somewhere else before we start this learning process. They're updated for every epoch. So whatever the training step ends up outputting is then going to be used in the second iteration of that training step, and the third and the fourth, and so on. And throughout, for each epoch, we're going to store the losses. We're going to store all the information in the forward pass. We're going to get our y-hat in the training, y-hat for validation. We're going to get our training loss or validation loss, and we're storing these so that we can complain about them later, or we can track them later. So here's our training loss, our validation loss, the epoch number that we're going through, and all of this is going to be stored just so that we can visualize it a little bit later. All of this is going to be stored in an pandas data frame, and this is where it's called, and this is where we, this is where this data frame is going to be visualized. Here it is. Oh, sorry, one more thing. I'm looking at the tail here. So like we used head a lot in data frame in order to see the first few rows of a data frame, just to do a sanity check often when we're just doing general data processing or data handling. But because we're more interested in the end of the process, like how did the training process end, we usually do a tail. So now we're looking at the last few epochs. So epochs 146 to 150. The training loss looks like it's continuously going down, which is good. So things are getting better and better on the training data. It goes from 0.3365 or 0.3366 down to 0.3344 at the end. Small changes, but nevertheless monotonically increasing or getting better. So they're decreasing. And the validation loss is also monotonically decreasing. This won't always be the case, but things are looking pretty good here. And it's decreasing by very small amounts indeed, but things look good. Here is nothing new. Here's just a simple visualization of the training loss and the validation loss over epochs. So literally, all these values were obtained by just running this function. I'll leave it to you to find out where actually. I'm curious. I'm sorry. Here's where I initialize the parameters. So I remember mentioning this, and I just forgot that this is already stored. Again, this is a Jupyter notebook essentially, so all these variables were initialized and stored appropriately and updated appropriately, and that gave me our training loss curve and my validation loss curve over here. So this is cartoonishly good. The 2 moons data set is super easy. Barely an inconvenience. It's so the loss generally, this kind of improvement is to be expected. When you're doing your own machine learning using this sort of general process, you're not going to see curves this smooth, just to warn you. What else are we doing here? Here is, I'm just taking samples. So this is not that, this is kind of redundant here, but I'm taking periodic samples in this, these curves. I'm taking it, every 30 steps. So I get the first step, the 31st, the 61st, the 91st, and so on. So I can get a zoomed out big picture of how things are changing, but I'm not really learning anything here. Although I'm putting all this together because I'd like to ask you to just write down and consider what you're seeing. Is training converging? 100% of you will get this. Does validation loss mirror the training loss? That is to say, is it sort of has a similar shape as the training loss? I think 100% of you will get this. And what might change if the loss is noisy or diverging? That's a little bit interesting. So you can take all this code I've given you and make some modifications, change the noise of the data set, change the initial parameterization, change any hyperparameters that we might have, including the learning rate, and then see if things change. Try to break this graph in some way, and then figure out what did I change in order to make this graph different or break. So a few more things. So we've done all of this kind of forward pass and backpropagation manually. So we kind of hard coded every step, of the process, and So like any good software engineer, machine learning engineers are like super good software engineers. We want to do a little bit of quality assurance. So before trusting that everything works fine, like the curves look fine, everything should be fine, I want to do some additional sanity checks, even if it appears that I don't have to. Maybe things are arbitrarily smooth or arbitrarily good looking, and I can't trust myself, so I want to do a quick test. So a typical way to test whether derivatives, like where your computation of derivatives is correct, is to apply small positive modifications to your parameters and small negative transformations to your parameters. So you have some small epsilon. You add epsilon to theta, you remove epsilon to theta. This difference of positive and negative change, right, this overall difference, averaged, like divided by or normalized by 2 epsilon, should be pretty close to your true partial derivative if epsilon is small, right? Because there's going to be very small local changes in your function. So like a little bit of a plus, a little bit of a minus, like, in a line between them essentially is going to be a good approximation for whatever the actual derivative is at that point for your big, fancy, nonlinear or complicated function. This is maybe a little bit of a microscope thing, but if you've taken calculus, you've probably seen that you can compute derivative by using very small local approximations, so that's what we're going to do here. So here is, let's see what's important here. I don't want to spend too long. I'm going to do some small permutations. So here's, everything's the same. Here's my epsilon. So here's like a small, like positive or negative, like a small amount I'm going to either add or take away from my partial computations. So I'm going to perturb v by a small positive amount, and this will give me a slightly different computation of loss. I'm going to perturb it by a small negative amount, and that'll give me a small change in the other direction. And then, yeah, actually, sorry, this is kind of silly here. So I take my true v and I copy it into v perturb, and then I add epsilon to it and I store it in v perturb 0. And the reason I have this minus 2 times epsilon is because I need to subtract both what I've added in the previous step and subtract it again in order to get like v minus epsilon. Okay, so if you're confused by this little step over here, I'm perturbing in the negative direction, but I've previously perturbed in the positive direction by that amount, so I'm just undoing that. So loss plus is the loss I get from adding a positive permutation. Loss minus is what I get from taking a small negative permutation. Down here is the difference divided by 2 epsilon, which is the local approximation I just mentioned a moment ago. And that's it. So like instead of computing like all of the like derivatives of sigmoids and the derivatives of these linear transformations like I did in math, slowly over the course of several slides, I'm going to do things in the more computational way of just looking at small differences. Okay. So if the difference between my backpropagation loss, which I did initially using a more theoretically valid combination of partial derivatives like I've been explaining this whole time, and I compare that to what I get by using this local approximation, which is dl dv fd. These should be very close. I want these derivatives to be as close as possible, because if they're very close, that means that the local approximation is the sanity check I'm doing currently is very similar to the more conceptual thing I did earlier, so here are those two values. They're kind of close. The local derivatives is 0, and the more conceptual one is 0.0438, 39, and so on. If this difference is still within the relative error that I've added, then I'm happy. And in this case, the epsilon is a lot smaller. It's 1 to the power of negative 5, which is down here somewhere. So, things don't look totally great. And I have to assuage you by suggesting that things are actually okay. We didn't make any mistakes. But this sanity check is nevertheless something we'd want to do. here is sort of a, not just one single sample like we saw a moment ago, but many samples over training data. We have, here's 5 indices. Here's our gradient-based backpropagation, or more conceptual approach. Here's the grad finite diff. Here's the relative error. Actually, yeah, so we are happy. Sorry, I misspoke a moment ago. This actual straight difference is bigger than 1 to the -5, which would indicate that something's wrong here. But the relative error is computed here. So it's sort of in terms of the local approximations, like the sanity check approximations. So how much of an error I'm making. There's this sort of bias term over here just to keep things numerically stable, so we don't get divides by 0. And everything looks good. The relative difference between the local hacky, local differential approach to taking the gradients in my loss function and what I computed using my backpropagation algorithm of partial derivatives is indeed always going to be smaller. All of these values are smaller than the actual value of epsilon, which is 1 to the -5. Okay, so things look fine. If errors are small, then the backpropagation seems trustworthy, and if they're large, there's some kind of bug. Worked example 2. So instead of manually implementing derivatives on every layer, we're going to use autodiff. We're going to just go ahead and jump to modern libraries and let it do all the work for us. This will let us, we'll define the forward computation graph, and we're going to get the framework to compute the gradients for us, given a scalar loss with regards to the parameters. So this is what your experience is going to be much more like. And we're going to use PyTorch, which is also what your experience is likely to be like. We're going to again use the 2 moons experiment, and we're going to look at loss curves. We're going to look at simplicity of code, and we're going to flag where we still need to be careful. So we need to set up PyTorch. So the first thing you have to do, of course, is to pip install torch, which is the library for PyTorch. We're going to import the neural network component, and we're going to use this tensor data set and a data loader. Torch also takes random seeds. We're going to keep on using 3151. And away we go. Nothing fancy going on here. We have a batch size of 64. So a couple of things I want to mention. So the word tensor comes up an awful lot. So what is a tensor, at least in terms of PyTorch? In PyTorch, a tensor is essentially a multi-dimensional array of numbers. It acts functionally very similar to NumPy's ND array. It'll have some extra powers to it. So under the hood, tensors can be moved to CPU or ideally GPU if available, allowing all kinds of optimizations. PyTorch can track operations on tensors, so a lot of the storing of intermediate values can be stored, so we can automatically compute gradients later. And there's all kinds of internal shapes like scalars, vectors, matrices, and batches of inputs. So everything we were doing before has a corollary in PyTorch. We're only using 2D and 3D tensors, so nothing really fancy going on. You can read more about PyTorch tensors here. If you want to know more about what tensors are generally, it's a little bit more complicated than what we're going to see, and it's a little bit more complicated than how a lot of machine learning handles tensors. Tensors are can be pretty complicated transformations of functions, and normally they're described in more depth in physics scenarios. So if you want to get deep into tensors, you're more than welcome to, but for now you can imagine that they're just serving the role of the NumPy's ND array. So this is what a tiny multi-layer perceptron looks like in the world of PyTorch. We will have 2-dimensional inputs. We'll have 8-dimensional hidden vector. we will have a sequence where we have a linear transformation. That linear transformation is then going to be passed through a sigmoid. That sigmoid is then going to be passed through a linear transformation, and then that linear transformation is going to be passed through one more sigmoid, and this will be the output of a forward pass. Right? So self-net is basically this sequence from the inputs all the way to the outputs. Very compact. This looks a lot like the pipeline we've seen previously, like just like a list of steps you take. This is how you implement a simple feed-forward neural network in PyTorch. So this is our class. We can call an object of this class model. We can set the criterion to BCE loss, which comes from PyTorch neural network component, and then we can choose an optimizer from Torch's optimizer subset. We can take the stochastic gradient descent. We have model parameters, and we have a learning rate, and that's basically it. This is all the setup we need to do for PyTorch learning of a simple feed-forward neural network. What does training look like? Using the PyTorch library. You can still, like, there's ways to automate a lot of this also, but just to not be totally automated straight out of the gate, we're going to have epoch, training loss, and validation loss, and we're going to kind of accumulate these so that we can report on them later, like we did previously in the fully manual case. We're going to have a number of epochs, defined here as only 50. We're going to train, and we have a running loss, and we have a number of train here. We will, this is a bit too detailed, so we need to clear the old gradients. So the gradients we computed in a previous batch, we want to kind of get rid of them. We want to then take the batch, which is we obtained from train loader. We want to pass that through our model, giving us our predictions. We want to compare the predictions with the actual outputs of this batch, YB, which again we get from train loader, which does our batching for us. So that criterion we defined previously as the BCE loss. Over here, sorry, here as the BCE loss. And we optimize using SGD, and this will store basically internally a lot of gradients and intermediate values. We'll have our loss, like our overall loss, multiplied by our inputs. Remember way back when, many slides ago, we had the derivative of L with regards to our inputs multiplied by the actual inputs. The derivative of the loss with regards to our weights connected to our inputs times the actual inputs. That's what's going on here, and then I just keep on, adding the number of training instances I've seen. XB is our batch, size 0 is the number of elements of that batch. I keep on adding to it. I take our training loss. This is our running loss computed in this little exercise here with our batches, divided by the total number of instances I've seen. And that's it. So I've done some training. I want to do a validation, so I want to see how well I'm doing on my validation set. Again, I'm not going to be doing testing yet. I still have access to training and validation through every single epoch, so I can look at both of these things and how they're changing over time. Everything I mentioned previously has a corollary here. I don't care about computing gradients now because I'm not actually going to use anything in a forward pass of the validation in order to update my parameters. I'm only going to update parameters according to my training data. Apart from that small difference, everything is the same. I'm doing batches using the validation loader, my same model, my same criterion, the same way I compute my validation loss and keep track of it and normalize it. And down here is where I just store the epoch and then the train loss and the validation loss over time. And then I'm going to store all of this, my history, in a nice data frame, which I can then look at in a few moments. Again, I care about the end of the training process, so I'll peek at the end using tail. Here it is. So I go through 80 epochs. How does that occur? I would love it for someone in the class to find what's going on here. because here I have 80 epochs, and there should only be 50, because that's what I passed into this actual function, which actually ran. So a little bit, oh, sorry, my mistake. I give myself bonus points. This is the default value of epochs for this particular function, but when I actually called it, I called it with 80 epochs right down here. So nothing mysterious, everything's good. Cancel red alert. Just like we saw before in the manual case, we have training loss, which is getting better and better and better and better. We have validation loss, which is getting better and better and better and better. So things look pretty good here. Here is a bit of a comparison. So I've previously computed the training loss for the and validation loss for my manual implementation for the same data set, and now I've computed it for using Torch through a number of epochs, and here are the two graphs superimposed over each other. I've done only 80 epochs for PyTorch. If I had set this value here at the bottom here to some larger value, this graph would be also larger. I mean, it would go on to the right a bit more. This is actually super fast to run. It might run on your laptop, so you're free to experiment with it as much as you want. But for now, I have some questions for you. Are all these curves fairly similar? If they're not similar, what differences might explain this? Do we have any changes in learning rate? Were there any changes in initialization? Any changes in batching? Any changes at all in our two implementations that can explain why Torch seems to be doing better than our manual implementation? And where, this is kind of more just asking for you to guess, but I guess where do you think PyTorch is doing the same math we did in our step-by-step graph-based computation as we did by hand a few moments ago? Our final comparison. So we're going to do a little accuracy function here to compare the ends of these processes. Our manual approach ended up with a training accuracy of 84% and a validation accuracy of 82%. PyTorch got a final training accuracy of 82.3% and a final validation accuracy of also 82%. So in the end, regardless of loss, our accuracies ended up being exactly the same on validation, which at least is comforting. Wrap up. So the key takeaways. This has been a long one. I was hoping to make it a bit shorter, but there's a lot of detail that I wanted to get through. We talked about the computational graph. So again, like a lot of the details of the computational graph was stuff we had previously seen already in our initial introduction to neural networks. We just have inputs being passed through layers, and layers being linear transformations of inputs, and then nonlinear functions on those linear transformations. So nothing new, just represented theoretically in terms of a graph, passing information forward when we're trying to make predictions and comparing predictions against reality through as loss. I wanted to mention this is not just for neural networks. I mentioned it at the very beginning. I'm mentioning it again now. This is within the context of neural networks, so everything we're doing is really neural networks focused, but the same computational graph approach can also be applied to other forms of graphical structures, including Bayes nets that allows for derivatives, for example. We did some manual derivations on toy models, so using just two hidden layers and using very simple models, we manually did step-by-step all of the details we needed to, so we're not just going to wash over things. Like, you deserve to know what we're doing in detail. I imagine some of you might have glazed over the second or third time we talked about the same kind of chain rule, but again, I wanted everything to be transparent for you, so we did that. The autodiff framework, like PyTorch's implementation, automates everything for us. So like in the PyTorch implementation in example 2, everything was much more compact. We said this is the sequence of events you have to deal with. This is the loss function I want to use. This is the criterion I want to use for training, and then you figure it out yourself, PyTorch. So it was much more compact, and therefore whatever augmentations or efficiencies are part of the PyTorch library that we didn't bother to implement, might be part of that library. Also, because the code is simpler for us anyway, we're less likely to make a mistake like we could have with that step-by-step manual implementation. In fact, like our manual implementation did end up with a relative error that wasn't great at the end, and we're only somewhat happy with, but still correct. If you want to try to find any bugs in the manual implementation, I think that's a great opportunity for you to try to learn, but don't spend too long on it because I double and triple checked the code and there shouldn't be any bugs in the actual manual implementation. Even if you're going to do a simple like library-based thing, if you're going to be like 90% of the population outside of DAO and just like taking libraries and using them without thinking about it, like you're going to have a bad time. So keep on doing careful modeling, like make sure every line of code is as correct as you can make it, do sanity checks, do proper evaluation and diagnostics, and understand, like it's always helpful to understand what backpropagation is. It's not just a term that you happen to see frequently. Backpropagation applies to learning and designing architectures, debugging any training that you're doing, and also engaging with modern deep learning research. Like a lot of like the manual implementation of these things is not something you're going to see when a library like PyTorch exists. But for those of you who are either going to go into deep machine learning research, you're going to have to open up the black box and implement your own ideas. If you want to do something very impactful, you're not going to be able to just stick the Lego blocks together. You're going to have to build your own Lego blocks at some point. So for those subset of you who are interested in that, I hope you gain something. When implementing or using backpropagation, we're going to care about a lot of things. We care about the correctness of all of our gradients. So being careful with our manual, the chain rule application is important. Doing unit tests and doing these finite differences, doing like those little sanity checks where we're adding epsilon and removing epsilon and making sure that that local approximation for the derivative is similar to our true computed derivative is going to be important. We want to keep on looking at training behavior, so always we want to, as whenever possible, we look at loss curves over epochs for training and validation sets. They should generally decrease, at least initially, and also with the caveat of noise. So different batches, especially for hard data, usually the loss curves aren't going to be as smooth as we've been seeing. They're going to be much noisier, but the overall trend should more or less be downwards, especially during the early epochs. But if things suddenly diverge crazily, or if that oscillation is much more than you'd expect, even in the dirtier data sets, you'd modify your learning rate, you would recheck your gradients, you would look for any bugs in the code. So like you start digging into your implementation. There's a couple of things you can do. So you can zero initialize your weights. This is a bad thing to do, but you can go ahead and try to do that. You can random labels. I think I mentioned this before also. So if you take your true values y and you just randomly permute them, you change some positives to negatives, you change some negatives to positive in your gold standard true outputs, and then try to train a model again on this totally randomized gold standard. You should not be learning anything because the labels are now meaningless. If your behavior is very similar to what you started with, to what you got when you messed things up on purpose, then the model is not learning anything. Maybe it's not your fault, maybe it's the data's fault, maybe the labels were wrong to begin with, but that's one of the sanity checks you can apply. And that's it. There are lots of bugs you can encounter. So like I mentioned it very briefly, but when you're using PyTorch and you're using batches within epochs, you have to remember to reset your optimizer, the gradients, to 0. Again, often you're going to be accumulating gradients, and if you're adding them over and over again through the training process, then it won't make mathematical sense, so you need to reset things to 0. This relates somewhat to when we were talking about the graphical structure, and we needed to take our partial derivatives, we set it to 0, and then we kept on adding things over and over again. It's somewhat of a different problem, but the same principle applies. You start with 0 and you add partial gradients after the fact. So you need to make sure you're summing over the right axis, that your forward passes are the same, that you're not mixing batches and feature dimensions, like all of the simple pandas data handling things that I just walked over quickly is done correctly. Occasionally, you might have non-differentiable operations in the path. So a sequence of steps during a forward pass might involve something like a argmax. Argmax is a very common thing to use or that we want to use in neural networks, but we can't train using argmaxes because argmax is not differentiable, so we can't pass information back through a graph in which there's an argmax. So that would break the process. So what can you do to get around that? That's the subject of future work. Yeah, so if you cut the graph, like if you do, before we did no grad when we did the validation, because I didn't care about, storing gradients during just a validation step. If you do that at the wrong point in the code, this can also cause problems. So just watch it. There's always ethical risks. So backpropagation and autodiff are technical tools, but just like with other neural networks, these are very complicated. There's very complicated steps, and we're doing the kinds of mathematics that most people in the general public don't know about. So if you're going to ship a neural network to somebody outside of computer science who doesn't have the mathematical background that you and I do, they're going to look at what's going on in your code and in your model and not have a single idea as to how to interpret anything. So, that's a problem. So we like neural network models, especially deep ones, because they're very flexible and they have capacity to learn all kinds of complicated things. But if you want things to be auditable or explainable to whoever the stakeholders are, this is a bit of a risk. There's these silent bugs and hidden biases. So if there are incorrect gradient implementations that are just slightly wrong, that you look at the loss function and everything seems fine visually, that can still hide the fact that there are errors behind the scenes. That's a problem. So everything looks good. You keep on doing experiments and everything seems fine, but there could be problems. This could mean that your deployment is going to be bad in some way. And also, of course, if your data is bad to begin with, your gradients are going to end up, storing information about that biased badness, and then that will end up with models that are biased and bad as well. Again, we're getting deeper and deeper into neural networks. You've probably seen through your own testing that even small changes to seeds can have big changes in terms of performance. Big changes to how you sample and batch can also have big changes. We have many parameters now. We have hyperparameters. We have, possibly parts in the gradient backpropagation where things might break down if we're defining our gradients manually. So we're getting pretty complicated in terms of our implementations. So all that complexity can result in reproducibility problems and accountability problems, like who is responsible for this gradient function might not be the same person who's responsible for designing a forward pass network structure. So you need to document everything. Use MLOps programs like MLflow, for example, and so on. And I can mention it right here. I should put a link here, but you've probably seen MLflow before. MLflow is a great library for doing MLOps properly. So we mentioned PyTorch. PyTorch does record all of the operations during the forward pass. Every tensor, every node will know what operation produced it. So like the directed acyclic graph we've hypothesized before is sort of how these modern libraries represent these deep neural networks. These computational graphs are built. There are nodes, there are edges. The edges are the functions. There are the partially computed values stored at the nodes. During a backwards call, there is a loss that's been computed using a function that we provide. We have the graph structure, so we can traverse the graph in reverse topological order and accumulate all of the gradients using backwards rules, and then accumulate all of these gradients and then apply them to our updates, to our weight matrices and our biases like we saw in the manual implementation. So obviously I'm glossing over a lot, but these modern libraries are essentially doing more or less big picture the steps we took in our manual implementation. You get all of this for free, so you don't have to compute all of the step-by-step modifications to every node and all of the partial derivatives. You get this for free from PyTorch, but you have to still make sure that your implementation in PyTorch is correct. Here are your quick checks, as per usual. Here are the small number of references we used in this presentation. This paper in Nature is, again, one of the preeminent ones. As always, thanks so much, and see you next time.